Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchala and I'm dealing with spectroscopy for chemistry. This is the lecture of IR spectra and lecture number 21. In this lecture, I will explain you Fermi resonance. Okay, suppose we take one molecule may have more than one functional groups. Okay, so there are various vibrations mode appear in this IR spectra. Okay, for example, we take one vibrational mode like this. This is V0 level, this is V1 level, and this may go like this. The energy required for this is about E1, okay, and this is fundamental vibration. Why? Because it is obeying selection rule. Suppose frequency of this is about say 1700, nearly 1700 centimeter inverse. Now there is another group which has different kinds of vibrational levels. Like this. For them it is V0 prime, V0, V1 prime, V2 prime, etc. When molecule absorb infrared infrared radiations, this vibration is also possible. Suppose the energy required for this one is E2. As vibration occur from V0 to V1, it is also fundamental vibration. And that is V0 prime to V1 prime. And for example, if the frequency is about 850 centimeter inverse plus or minus 10, okay, then it is fundamental vibration. Now this fundamental vibration or this functional group, particularly this functional group, may absorb more energy, and so that the vibration mode brings molecule from V0 prime to V2 prime, like this, and the energy required is maybe E3. Now this will be a first overtone of fundamental vibration. Now this E3 will be about 2 times E2, which is almost equals to E1 by chance. Follow? So in this case you can see that E1 is almost equals to E3. Now in this case we can say that these two are having equal energy. The fundamental frequency or fundamental vibration E1 or V1 and fundamental vibration, first overtone of fundamental vibration E2, that is E3. So this may be having same energy. So we can say that it may happen that two different vibrational modes in a particular molecule have frequencies very close to each other and have nearly the same symmetry. They are described as accidentally degenerate modes. So this type of name is given to these two vibrational modes, that is E1 and E3 become accidentally degenerate modes. It is generally found that most often between a fundamental vibration and some overtone or combination vibration. The two vibrations interact with each other. By a typical quantum mechanical resonance to give rise a pair of bands, which is called a doublet of nearly equal intensity and the frequency of one is raised and the other is lowered. Why? Because they exchange their energy, vice versa. And therefore, each vibration is now has partial fundamental and partial overtone. Thus, splitting and formation of a doublet is one phenomenon which is known as Fermi resonance. Okay, so this is called Fermi resonance, and a doublet is known as Fermi doublet. Fermi resonance is always between a fundamental vibration and one overtone or combination vibration. Okay. For example, if we take aldehydic hydrogen, CH bond. Okay. So this will appear like this doublet, and which will be 2827 centimeter inverse. This is for CH stretching, and another is at 2725 centimeter inverse. This is the overtone of CH bending. Okay, and therefore these two appear like doublet. So this is a doublet, and it is because of Fermi resonance. So this is also known as Fermi doublet. Okay, so here normally aldehydic CH stretching vibration usually appear as doublet due to interaction between CH stretching, that is fundamental, and overtone of CH bending vibrations. Okay, there are some more examples also, like in carbon dioxide also we can explain. In CO2 there may be a doublet appear at 1388 centimeter inverse and 1286 centimeter inverse due to Fermi resonance. So that's it in this lecture. Thank you so much.